All right, ladies and gentlemen, welcome to another CLSP seminar. Today's seminar speaker, Chris Bartels, is known to some of us because he was here 2 summers ago. It was still 2 summers ago.
2 summers.
Time flies. Anyway, so he was here as a summer workshop student, and he worked in Carol Devescu's team working on articulatory models for speech recognition. Chris is close to finishing, and he's interested in postdoc opportunities, and we thought we'll grab him before the rest of the market sees him, so we got him here early. Chris works on graphical models, like I said. He's at the University of Washington, and his work is being supervised by Jeff Bilms, whom, again, some of you know. In particular, Chris is one of the key people in developing GMTK, the toolkit. And within that, he worked on various algorithmic aspects of triangulation and inference in general in graphical models. And he's particularly interested in applying it to large vocabulary speech recognition, which is still somewhat of a challenge, although it's getting there. And I believe today he'll talk about things related to that, right? Yes, Bayesian networks for automatic speech recognition. Chris?
Great, thank you. All right, as I mentioned, I'll be talking about some recent work we've done on applying dynamic Bayes nets to ASR. It will be the first portion of my talk. I will introduce graphical models. I will talk about the triangle structure and how it can be used to process sequences. And then finally, I'll talk about a few applications of graphical models and the triangle structure to automatic speech recognition. The second part of my talk, we'll talk a little bit about burst noise and why burst noise is a problem for speech recognition. Then I'll talk about what is a syllable, and then I'll talk about a specific graphical model that integrates a syllable recognizer with a standard speech recognizer. And then finally, I'll show you some results that show that this particular graphical model can improve the word error rate by reducing insertions due to burst noise. And then my second part of the talk is a little bit of a switch, but it's related, and I'll be talking about some of the improvements we've made to speeding up and reducing the memory requirements in making probabilistic calculations in graphical models. And there's really 3 aspects to that. First is called boundary search, which is a triangulation method. The second is the use of non-minimal triangulations when we have deterministic variables in the network. And then finally, I'll touch on some work primarily that I want to work on how to make use of sequence structure when doing inference. So, some acknowledgments. This work is joint with my advisor, Jeff Bilms. And you can see some of the work on the burst noise in our recent ASRU paper and interspeech submission. And then the work in inference, you can take a look at those in this list of papers. OK, introduction. OK, so what is a graphical model? A graphical model is a class of factorized probability distributions. And one of the prominent features is that they have a visual formulation. So you have a factorized form of the probability distribution, and then you have a visual formulation, and you can go back and forth very easily between the two. So why would you want to use this? Well, factorized representations lead to constrained parameter learning. So if you have a function on 3 variables, you're learning a 3-dimensional table of parameters. If you're able to factorize it, you're learning a 1-dimensional table and 2 2-dimensional tables. So you have order of magnitude fewer parameters to learn. Second, sometimes certain factorizations lead to conditional independence. And when you have conditional independence, you can do inference faster and with less memory. Given a standard Markov chain, you have A is independent of C given the B variable. And as I had mentioned, when you have conditional independence, it improves inference. And this results in rapid exploration of a lot of different distributions. You make the change on the graphical model level, and the inference engine figures out how to exploit the conditional independence in your model. And then finally, it facilitates communication and design. Looking at this model, it's very easy to tell someone what you're doing and very easy for them to figure out what you're doing. And then once you see it on paper, sometimes that helps you come up with new things to do with your model. OK, what is a Bayesian network? Very quickly, there are 2 prominent graphical model semantics, undirected models and directed models. Bayesian networks are directed models. There are more semantics, chain graphs, and more, but these are the main two types. Directed models are nice in that they're conducive to generative modeling, and they have conditional probability tables are normalized, which are very nice. Okay, so what is a dynamic Bayesian network? Well, simply, it's a graphical model that has a template, and this template unrolls to match the number of observations you have. So we have a template, and here we have the template unrolled to 3 observations. So in speech recognition, we're all familiar with the hidden Markov model, or the HMM. The HMM is actually an instance of a DBN, even though DBNs came later. And you can, in HMMs, you can do efficient calculations because you have this conditional independence property. Forward, backward, you have past is independent of the future, given the present. This particular model has 1 state variable per frame and 1 observation per frame. So in speech recognition, these state variables, Q of t, they encode a large variety of information in 1 giant state variable. That single variable encodes the word identity, it encodes the position within the word, such as the phone and the subphone state, and it also encodes your language model history. So with a DBN, what you can do is you can take, instead of having that single state variable, you expose that high-level information by using a network of hidden deterministic variables. A very simple example of this is the triangle structure from Zweig and Russell in '98. And this is just a model that's equivalent to an HMM, and I'll explain what we can do with this simple structure. The triangle structure can be used for finding phone alignments. So this problem is where you have a word in pronunciation, you know what they are, and you have a deterministic sequence of phones. You have some stream of observations that's longer than your stream of phones, and you have to decide which phones go with which observations. Very simple example, the word cat, pronunciation ka, a, t. Then you have 10 frames of audio data, and decide how many frames to assign to each of these phones. So using the triangle structure, here's how it's done. You have a position variable. This position variable just counts. It's an index into your phone stream. So it just does 0, 1, 2. You have a transition variable, which tells you true or false, are you on the last frame of a position? So it hits true here, here, and here. Then you have a state variable, which gives you the identity of the current phone. And you can see those. And this is separate from the position variable because you might have the same phone appearing twice in the same word or across words. And then finally, the observation variable. And the same thing can be done with an HMM. It's just that we have this high-level information available to us. Once we have this high-level information, it allows for logical and simple extensions. Okay?
So what would be the path that would have those 4 zeros over there?
Sorry, these 4 zeros?
Yes.
Okay, this is the transition. So transition is true when you're in the last frame of a state, and it's false when you're not in the last frame of a state. So K, we're not in the last frame of K, so it's false. True, because...
No, but I thought you will tie it to the...
Yeah, but the graphical model.
Okay.
Does it relate?
So
Okay, so the graph isn't showing... I'm only able to fit 4 frames on the screen. So there really should be, say, a dot, dot, dot.
actually,
And then,
you could show the first 3 frames of this picture with the 3 blue circles there, and maybe that will clarify.
yeah, so this is really only 3 frames of the graph. It really continues out as there's one of these triangles for each observation. So there should be 10 of these triangles. It just doesn't fit on the screen. Does that clear up the question?
Yeah, that answered my question.
So I guess, Fred, what's happening is that the white circle is the transition variable. And in this first frame, the white circle has value 0. So that the upper red circle in the second frame is the same as the upper red circle in the first frame. In the second frame, the white circle has value 1. And therefore, the red circle on the top in the third frame is different from the red circle on the top of the second frame. And that change was triggered by this transition variable saying I'm 1, and therefore a transition needs to happen in the position variable.
Does that mean that we did not go through the first white circle and we only went through the second white circle?
These are not states. The pictures here are not states in an HMM.
These are random variables, and they take values.
Yeah,
The value is the state, but the values aren't shown here.
yeah, these are showing conditional independence properties of random variables. It's not like a finite state transducer diagram where we're showing the grid or through the states.
So what's the value of the arrows on the top line between the different states? Is there any value there?
So this is saying which variables does the value of position depend on. So it's set to 0 in the first frame. In the second frame, it will copy the value from the previous position if this is false. If this is true, it will add 1 to the previous value of position.
And more generally, Chris, you should probably emphasize that the two arrows leading into the top red circle of the second frame essentially say that the random variable in the top red circle of the second frame has a conditional probability table in which the conditioning variables are the values in the top red circle of the first frame and the value in the white circle of the first frame. So there is such a table somewhere. And in this case, it happens to be a degenerate table, which simply says if the white circles are 0, all the probabilities on whatever the red circle was. If the white circles are 1, I guess in this case, you will increment the position by 1.
Yes, so this position is really a deterministic function.
So in a classical HMM thing, that would be the self-loop, the light would be corresponding to some
So
self.
yeah, the self loop would be transition equals false. And you can see if you go back to the other HMM, you have these three variables are your giant state variable. If you're doing an FST transition diagram, you have a self loop for false and an arc to the next state for true. Okay. All right. So once we have it in this triangle structure format, it allows for easy extensions. This is the same graph as last slide, only just a little stretched. And this is just an example of something you can add to such a structure. We have a hidden variable that gives you some sort of state describing the current speaking rate. Then you have some sort of acoustic observation telling you something about how fast the current speaking rate is. And this graph was also due to Zweig. Another extension is, well, most of the time you don't just want to have one word. So you can add some sort of a random variable that randomly chooses a word. Then you can change your state sequence depending on what type of word you're on. This is a bit of an oversimplification, but gives you the general idea of how you can extend this basic 4-variable structure into a generalized recognizer. Okay, so some of the work I've done in the past used DBNs for modeling asynchronous streams. So the idea is you have multiple streams of subword states. For example, in audiovisual recognition, you have one state correspond to phones seen from the audio data. Then you have another set of phones that are derived from video features. And then at the beginnings of the words, these are forced to be synchronous. But since articulators can anticipate audio data, allowing these to be a bit asynchronous showed some improvement. And then there's some other work on audio-only features, and then some additional work from our workshop on articulatory modeling where the asynchrony was in human articulators, both for audio and audiovisual. And then another class of graph is something that we call focused evidence. The idea of this is you don't add any additional state to the model, you just add additional observation streams. And the DBN allows you to condition these variables directly on some higher level piece of information. And we have a couple of examples of this. Okay, now we're moving on to the graphical model for burst noise suppression, and I'll go into detail about this particular model. But first, I'll describe the problem. Okay, burst noises are unexpected sounds. Very commonly, you have breath and microphone sounds. You have crosstalk from telephone receivers and from multiple mics in say meetings data. You have background talkers who are intended to be on the channel, and then you have whoever's talking doing things while they're talking. You could have typing, animal noises, shuffling papers on the desk, things to that effect. And in recognition systems, these types of of sounds are often just decoded, erroneously decoded as words. This particular problem is difficult because it's not speech or silence. These particular noises aren't labeled in your database, and there's no training instances of lots of particular noises. They might be very rare. Previous work in noise robustness has concentrated in a few different areas. There's quite a few papers on voice activity detection. This is important for things like cell phone coding. But more specifically, in speech recognition, there's been some work on integrating voice activity results into a speech recognition system. And primarily, we differ from this in that we're detecting noise at recognition time. We're not taking some sort of feature output from a second system. And then there's another line of work on noise-robust features. And we differ from this work in that noise-robust features are generally more applicable to a stationary noise in that they either do some sort of smoothing or have some sort of a background model that helps with that type of noise. Okay, one particular characteristic of speech that we exploit in this work is that speech has a syllable length modulation. That's just the rhythm or energy pattern of speech, and it occurs in about 3 to 6 hertz, depending on the speaker and the situation. And perceptual experiments have shown that this particular modulation is actually important to understanding. They found ways to remove this and showed that it degraded perception. And more importantly, that noise generally does not have this particular pattern. So our method is to combine a conventional word recognizer that uses phone models and a syllable detector. And the goal is to reduce insertions from burst noise in speech recognition. And real quickly, some related methods is we have Wu used some syllable detections to prune down a lattice. And our work is different in that we're actually using a DBN, so we can do this across all hypotheses, not just the lattice hypotheses. And our improvement is from speech noise discrimination. And Basu 03 did some work for joint speech decoding that was similar, but was more geared towards voice activity detection. Okay, the anatomy of a syllable. Generally considered to have 3 parts: an onset, a nucleus, and a coda. The nucleus is the center of the syllable and is the vowel. It's also notable that it's the point where the syllable is the most sonorant. That means it's at its loudest and the most resonant. The onset and coda, they don't always exist, but when they do, they're consonants. And the most sonorant of the consonants, they directly surround the vowel, and they become less and less sonorant, less and less resonant the further you get from the nucleus. So what we're going to do to find nuclei is we're going to measure sonorance, and then we're going to find maxima in the sonorance measure. So here's an example. The utterance is silence, O, OK, followed by silence. And then we have some sort of measure, and then we take the maxima. So there's 3 syllables, O, OK. So how we estimate sonorance, we actually train a set of neural networks to detect vowels. Then we take the posterior of the vowel and smooth it, and this is the sonorance estimate. And it's notable in our system, sonorant just really means vowel-like. We're not actually detecting resonance, but it's a sensible definition in that the sonorant consonants are more vowel-like than the non-sonorant consonants. And here's the estimator. Here's a diagram. So you have audio data, you generate PLPs, then you put them into a neural network, then that outputs posteriors, we smooth them with a 9-frame Hamming window, and then we have that sonorancy estimate. Okay, and then this is similar to, but different from a few other methods that detected syllables. Primarily, these methods threshold based on some sort of posterior, and our method is doing this peak finding. Okay, back to the DBN. So we have a standard phone-based recognizer, and then we have a syllable counting stream. So I'll hit this in more detail, but what's going on at the high level is that for each hypothesized syllable coming out of the recognizer, you're going to count the number of detected syllables. And I'll show this graph in a little more detail.
Did you work in multiple languages or only English?
Only English. Okay, this is the
Which languages in particular
Yeah, you'd probably have some issues.
The traditional problem with the sonorants hierarchy is sibilance. Do they give you trouble, or you're able to account for them with the sonorancy metric?
I guess I haven't measured that. The fact that we're using neural networks to detect vowels rather than actually recognizing some sort of resonance, I would think that we are...
So you have a sonorancy estimator that's not fooled by sibilance.
You know, I probably shouldn't say anything because I haven't actually
Okay.
looked at that for sure.
What is the accuracy of your estimator?
Yeah, so I don't have syllable markings in the data, so I don't know for sure, but I do have train parameters based on what percentage in the training data do you hit this detection given expected, and it varies depending on how I tune the particular parameters, and this is actually an accuracy, it's a soft accumulated count. And the system that works the best, it's really only about 62% accurate, and I'll talk a little bit about why that's not so bad. If you tune particular things, you can get it up close to 70, but then another nice property of it goes away, and I'll talk about that in a bit.
But Chris, could you measure it something like this? You take some speech for which you have transcripts, and you take a reasonably good phone-based HMM system, do a forced alignment so that you actually have the start and end time of each vowel, and then every time you get a peak which is inside that range, you count that as a hit. And every time you get a peak outside one of those windows, you call it a false alarm. And every time you don't get a peak, a hit inside that window, you say you missed that vowel. And you just measure some sort of
Yeah, certainly that would work.
precision recall. Would you, I guess you haven't done this, but if you did that, can you speculate what?
I would suspect it's fairly close to the trained probability. The main reason is we use, in training, we use the Mississippi State word alignments, which give hard boundaries on the start and end of the words.
Right.
So really the only soft accumulation comes from multiple syllable words as far as where those hit. So for the one syllable words, you're actually going to get the right number of counts in each word. For multiple syllable words, it's going to be reasonably, accumulate reasonably accurately.
All
right. So this graph, at first glance, it appears fairly complicated, but it's really not. So I won't. This is just a baseline phone-based recognizer. I won't go into the details of this, but just at a very high level, you can see a triangle structure, and then you have a word and a pronunciation variable, and then a word transition. If you're more interested, I can refer you to a few papers, but for now, just view this as a word-based recognizer. This upper portion is a syllable counting stream, and I'll go over all of these variables in detail. Okay, the top variable these are our estimated nuclei. So these are observations, and they're observed to be either 0 or 1. Most of the time they're 0, and then when you hit that frame that's the peak in your sonorance measure, it's set to 1. This is the syllable count. This variable is the total number of syllables, the total number of detections since the beginning of the hypothesized syllable. So it's an accumulated count. This variable is the syllable transition type. This gives us two pieces of information. It tells us whether the bottom of the recognizer is transitioning out of a syllable and what the type is. So more specifically, it takes on 4 different values. Most of the time, it's this value, meaning there's no transition. It can also indicates whether in the last frame of a silence, the last frame of a short pause, or in the last frame of an actual speech syllable. And again, this is a 0-1 variable. And one of the functions it performs is to reset the count, so that this count is reset to 0 when we reach the last frame of a syllable in the previous frame. This variable called count matching. What this models the distribution of detected syllables given the expected number of syllables. For example, in speech, we expect there to be 1 detection per syllable, and then what we see is a high probability, about 62%, of actually seeing that detection, and then a lower probability for 0 or 2, and then an even lower probability for 3 or more detections, and similar things for speech, or for the silence regions. And finally, we have the count consistency variable. Without this variable, this would just be floating. It would never affect the model. What this does is whenever the syllable transition type goes from into any of the transitions, meaning it's not no transition, it's a constraint that forces the syllable count to match the count matching. And essentially, this multiplies in this probability table, and it's evidence so that this distribution can actually affect the model.
So this is the count in the syllable that just ended. What are you checking consistency on?
So so if you're in the last frame of a syllable,
Right.
it forces that this actual count of observations,
Okay.
and then it forces this hidden variable to match that count.
Right. Okay.
So without this variable would just be summed out, and it would not affect the observation. This is an instance of virtual evidence that connects these two variables together. An easy way to think about it is for every hypothesis in the frame where the syllable ends, it multiplies in one additional probability table, whereas when without this variable, it would not multiply in that probability table.
And when the syllable transition type is null, meaning there is no transition happening, there, even though the consistency value is always observed to be equal to 1, no check is being performed.
No check. So this arrow, this indicates that it's essentially turning this check on and off. So.
Okay.
And this is the same graph you saw before. I'm just putting it up again so you can see how.
The dotted line, the switching parent thing that you guys have?
Yeah, that's a detail I
No,
glossed
it's
over.
okay.
The dotted line is a switching parent. Yeah, allows for value-specific conditional independence. Yeah, so here's the syllable counting stream once again, and how it integrates into the lower part of the graph. Okay, the experiments were performed on the 500-word task of switchboard.
Just go back for a minute. Let me
Okay.
make sure I followed this basic idea.
All right.
So the lower white slab, uncolored one, is your standard phone recognizer.
Yes.
And every time your phone recognizer goes through the end of a phoneme, if it also happens to be the end of a syllable, the lowest red circle says 1, saying I have reached a transition point.
Yes.
And then the upper red circles are counting. They were reset the last time there was a transition. And they have counted how many. If I think of these syllable nuclei detector as blips on some kind of monitor, they count how many blips I've seen so far.
Exactly.
And so when you see end of a syllable, the white circle is told check whether the number of blips matches what you expect.
Yes.
And the one variable says they better match, and you take a hit if they don't, according to the probability of the mismatch.
Yes.
And that's your joint thing. And so there are two observables in this: the actual speech down here, which your phone recognizes doing, plus the blips, which are counting syllable nuclei on the top line.
Yes.
Okay, good.
Exactly. Okay, the experiments were on switchboard, and this is a subset of switchboard 1. So this is actual conversational telephone speech. We get 500 words by extracting a subset of the utterance, so that we're only using utterances that are part of this closed 500-word vocabulary. It allows us to do faster and more experiments, but still use real conversational data. All the parameters, including the neural network, were trained only using this data from the switchboard training set. The neural network was trained with regularization using software written by Xiao Li, and all of the training and decoding was done using the graphical models toolkit. Okay, recognition results. Have a baseline word error rate of 51.9, and we get an improvement to 50.8, which is 1.1 absolute and significant at 0.02. The second result is using the same two graphs, the decoding and the syllable level, but in addition we add a frame level silence oracle. So we took the transcripts and we let the recognizer know exactly which frames are silence, then it's only left to decode the speech within the speech regions. And you can see the results here are approximately the same. So you can tell the improvement from the previous slide is coming during the silence regions. So that's where.
Right, thanks.
is the training and dev and test sets?
It's approximately 3 hours for train and about 1 hour for dev and 1 hour for tests. Okay. Then finally, this slide, these are results I showed before, but it shows, if you look at the baseline, look at the syllable graph result, and then look at the baseline plus silence oracle, this shows that we're achieving about 50% of the oracle rate, considering just the silence regions. So how does this work? So this is an actual utterance from the database. What we have is silence, followed by the word right, followed by about half a second of a breath noise, then followed by more silence. The baseline recognizer decodes this as silence, then it gets the first right correct, and then it decodes the breath noise as the word right. And then this is followed by silence. And then the syllable decoder, it decodes this whole region as silence, which is the desired behavior. We're not actually labeling noises. So this is what we want to see. Okay, here's the output of our sonorance detector. You can see during the region of the word right, it correctly finds one syllable. But you can see during this noisy region, there's a large number of false positives. So there are times where this gets a fairly high posterior for being a vowel, but this posterior raises and lowers at a rate that's much faster than a typical rate of syllables, and more often than the one syllable word that the baseline recognizer decoded.
So Chris, just take this. So I mean, it's probably not correct to think of the DBM taking decisions in time because it's an overall inference. But I would like to think that at something like 1.1 seconds, that combination, the consistency check variable was turned on, and the top line said I expect to see one syllable, and the lower line said I have seen 5 syllables, and that said, this is terrible, and it got a very low score, and that's when that hypothesis got killed.
Yes.
Is that okay?
Yes, exactly.
That's the way to think about it. Okay.
Yes, and it's a.
But if there had been other hypotheses, just stay up again.
Oh, sorry.
So if there had been another hypothesis which said that at 0.85 seconds a word has ended, then that hypothesis might have stayed alive because, hey, 2 syllables instead of 1 is okay. And then if there was a third word hypothesis, that could have stayed. As it happens, the silence was the best hypothesis alive.
Yes.
But there could have been some other, if there was another fit which hypothesized more than one word in that region, that could have survived instead.
Yes, absolutely. And if that did happen, this would actually reinforce the incorrect hypothesis.
Right.
But in general, that doesn't seem to happen. Usually the noises cause one syllable word because it has to match the fewest phones possible, or possibly 2 syllables.
Right.
And then you get these false detections because you don't have this nice slowly becoming vowel-like and then slowly not becoming vowel-like. You just get, there's a few points where it actually kind of looks like a vowel, but it doesn't transition in and out of the vowel at a 5 hertz range like you see in speech. Make sense?
Yeah, from what you just said, and also as a way of excluding multi-word hypotheses in the silence here, I'm guessing that you don't have a simple exponential decay as your duration model. I mean, that's what you've been describing on the slides, I think.
So the recognizer itself does have a simple geometric distribution. It's each state is at each frame you have just a binary transition, which ends up to be geometric. But you mean the joint model?
Maybe I take it back that you need something more than that.
So the basic recognizer just has the standard duration model. One way to view the syllable model is to say that it's adding something to the duration model. It's using some sort of acoustics to improve the segmentation, but I'm sorry, I'm not sure if I.
Well, your prior on the durations is still fairly simple.
It's
duration of any state.
It's just a simple frame by frame transition probability like you typically have.
Do you have any intuition about whether it would help to have a gamma distribution over durations or something? I mean, I understand that would be a little harder to model in this framework, but.
I don't think it would work. Yeah, so this is a bit of an aside, but in some of the work leading up to this, I had some earlier work that put some evidence on the transition variable. It was basically using just the deltas and using a simple distribution. Anyways, I did some Oracle experiments on the state durations where I took the number of phones per frame and tried some scaling of the state distributions, and it didn't really help. But if you scale things like the word transition probabilities, that Oracle information does help. So I guess I haven't done a lot of experiments, but the little experience I have and from just conversations, modeling better state level duration doesn't seem to be a big win, but maybe there's other people who would disagree. So,
When you say other people, it's not a big win. You don't mean in this. You don't mean for a model that's still in the course, though. Right?
I just mean I don't know of a lot of work of people who have done speech recognition experiments where they've done better state level distributions and gotten an improvement. Is that?
You are or are not using the Zweig rate variable?
I am not using the Zweig rate variable. That was just an example of something you could do. In fact, I'm not aware of anyone who's actually tried that particular experiment. Okay, and yeah, I think I touched upon these in our questions. Right isn't 5 syllables, so that hypothesis gets downgraded. The correct right has 1 syllable that's correctly detected, so it's reinforced. This improvement comes from a mismatch between the classifiers, and this particular mismatch is recognized as non-speech, and it's not from a particularly good acoustic match between the training and the test data. So theoretically, if you had a noise that wasn't seen in the training data, you'd still get false detections, and you'd still be able to classify this as non-speech, even though it's not in the training data. The switchboard data doesn't have noises marked, so it's not something I could test, but I'd like to hypothesize that that's going on. Yeah?
Is this the motivation for counting syllables? In other words, we count syllables as a check on whether there was speech or there wasn't speech? Because the regular speech organizer would have assigned something to that region?
So actually, to be completely honest, this was not the motivation for the original motivation for the model. It was really to see if you can add in information about segmentation and duration that's not in the HMM. It's kind of as a cheap duration model, and then when I tried it, I saw these improvements and tuned it.
What does it do us?
Well, if you have, say, a closed captioning system, and you have someone, and there's some sort of background noise, a car crash, and this particular noise, you don't have a car crash in any of your training data, so your recognizer might spit words on the screen and say a car crash is someone saying hello, which probably isn't.
But that's why I said that this is the motivation for it. So is there an
Ex post facto.
Yeah. What Chris is saying
Well,
is,
somebody must come up with saying, I'm interested in syllables. I don't care
Well,
about
there's all kinds of
syllables.
things syllables could do for you.
Say again?
There's all kinds of things syllables could do for you.
Could do for you, but this is where we see an improvement.
So you're saying that the original motivation was in fact something like, well, if we have this surrogate for syllable occurrences, syllable epochs, then maybe our word recognition will improve by replacing the wrong word with the right word. And what you found is, hey, but it does something more that we weren't expecting, namely whenever there is non-speech, it's clearly telling you it's not speech. So more than helping the recognition for its own sake, it's helping you get rid of, and I think the last point is maybe the main point, that all kinds of noise, including noise that you haven't seen in training, will have this property that this detector will not like them.
Yes.
So in some sense, it can, like Jack said, post facto be the real motivation.
And so actually, I touch a little bit on this in the next, well, okay, hit the slide real quickly. So what is the DBN doing for you? You have this hidden variable that models syllable counts, and this adds additional state to the model. And this additional state, it can model variation on a time scale that's longer than the frame rate. So it's modeling it, the number of counts across the time scale of a syllable. And the count changes with word boundaries, and it can be an exact word boundary according to the hypothesis, whereas something that's smoothed over detections would smear that detection across the word boundary. Okay, the future of this work. I can have some results. I'll show you some results that even larger improvements are possible if we can detect the syllables better within the speech regions. So I generated some oracle features by doing, I found oracle syllable boundaries using a forced alignment, and then I defined the syllable nucleus as the center of each syllable according to the forced alignment. Then I create these 0-1 features using this data. And, oh, yeah?
Are the syllable boundaries, the number of syllables lexical or actually pronounced?
It's lexical, so it's the number of vowels in the pronunciation. So if you don't follow the pronunciation, then there's going to be a mismatch.
And so what you're doing now is that sequence of beeps that used to be automatic detections now are real things.
We now have the information from the transcriptions. Right. So you have the exact number of syllables, plus roughly, according to the canonical pronunciations, you have the right number of syllables, and you know, at least within the range of the syllable boundary where they are. It's not exact, but it tells you 1 point in the data where that syllable center might be. And the improvement using these oracle features is quite large. We get 9 points of improvement. So this shows that if we can improve the detection in the within speech regions, there might be some big wins. Possibly use multiple estimators so that we can keep this win from the speech detection. And there's a lot of areas to try. In particular, the front end to the syllable detector is something more interesting than PLPs that can actually measure resonance. Yeah.
Just to understand your results, so if you were to, what you have now is 15.8, but you show that you could do really 42.5.
Yes.
If you do a better job in detecting syllable boundaries, whatever.
Yes. Yeah. And this is specifically within the speech regions. Yeah, so that's why I kind of tried to rush into this, was to show this result.
So have you looked at all to see whether the errors in syllable counting are due to the fact that they were never pronounced, as opposed to pronounced but not detected?
Yeah, I've looked at that somewhat, and it just seems to be get more anomalies. Just false detections and misdetections more than the pronunciation not matching the canonical. So typically it's the number of syllables is, according to my system, the number of syllables is the number of vowels. And that's typically not, you can have dropped phones, but you don't have dropped syllables very often. You do get into trouble on words, in particular the word really. In our dictionary, there's two pronunciations. There's really, and then there's one that's really. Listening to those, I've never, even though it sometimes thinks it's really.
Well, this is a trick question. Linguists are always asking how many syllables in fire, and
yeah,
things like that.
Yeah. So I mean, these are all good questions, and all questions I don't have a great answer to. But in some sense, the model does have a little bit of ignorance of what is a syllable built into it. It just, you have this probability of how many detected versus how many expected. There's also some error in the how many is expected side of it, and this is going to be reflected in this distribution. You obviously want this distribution to be as low entropy as possible, so if you can better predict the number of syllables, that would help as well. But I think right now there's more room for improvement just on the detection side than there is on the expected side, even though there is some ambiguity in defining what is a syllable and how many would you expect to see.
So in the oracle case, is it still the case that you're reducing the number of insertions? Or is it you're actually making corrections to substitution errors and deletion errors or other types of errors?
Well, funny, it's actually difficult to interpret. So insertion errors does drop a lot. What's kind of strange is you, see if I remember this correctly, I believe you actually get an increase in the number of, it was either an increase in the number of deletions or number of substitutions, but it was because it was, if you look at the baseline, it was just changing the hypothesis so that you got the other instead of, it was doing a lot of exchanges of deletions for substitutions. So it's mainly substitutions and deletions that are the result, but the numbers don't. Just looking at the transcriptions, yes, but if I showed you the number of substitutions, deletions, and insertions at the best possible word insertion penalty, it wouldn't exactly show that. I'd have to show you alignments to convince you of that.
The Oracle experiment has oracles both for training and for testing?
Yes. So the parameters, in a sense, are perfect. Given that you expect one syllable with probability 1, you're going to see one
You
syllable.
get something in between these numbers if you only consider oracles for the test or only for...
Yeah. I would imagine it would do very poorly if you only had oracles for the test, because it would, with probability 1, it would be inserting words. But if you had it only for test and estimated and train, I would imagine it would still see an improvement.
So, to just paraphrase what you say, is I think most of the gain is from training, having really more robust training.
No, that's not what I was saying. I was saying since you have them both in training and test, what happens?
Match conditions.
You match conditions. It says with probability 1, if you have it detected, you must have one syllable coming out of the recognizer. And if you had estimated in test, it's going to make a mistake every time there's a false detection. Okay. All right. So, sorry, what time am I supposed to?
You have about 12 minutes.
Okay. So this, I had a lot more questions than the practice talk. So, so I have a whole nother portion of the talk. I think maybe I'll just touch upon this boundary search problem. I think a number of you in the room have seen this talk on non-minimal triangulations. This is a very important part of my thesis, and I think it's great work, so you should all go read the paper. But we'll...
I have a generic question on your graphs. I don't know if you're going to talk about it, but
Okay, go ahead.
some other talks that I've seen on this, apparently when you have graphs that are really so complex, and they have arrows going laterally as opposed to just one direction or one direction. I mean, the computational aspects of it are not trivial. Are you going to talk about that, or?
So one of the things that, if you notice
I don't mean to change your talk.
Maybe we'll talk a little bit more about this offline, but one of the main reasons is you have so many deterministic variables in your graph. If you clump these variables together, you can just determine their value as functions of other variables, and just the random variables themselves define the state. So I'll talk to you offline about that. Okay. So I have to do this quickly, but speech and language graphs, they model sequences. So what I mean by sequences is that they have the triangle structure that I talked about earlier. And this triangle structure is used to model some sort of high-level object that's defined by a deterministic sequence of low-level objects, such as a word is defined by a sequence of phones. And this gives a few unique challenges for inference. And what I mean by inference is decoding and training the calculations associated with these two tasks. And the one thing I'm going to try to talk about before we leave is how we can perform inference tasks faster and using less memory. And I'll talk a little bit about triangulation boundary search. And then, sorry, but I'll skip these sections. So what is triangulation? This is very brief, but triangulation is a graph preprocessing step that's required for inference. So the choice of triangulation just changes the amount of computation and the amount of memory it takes to compute these probabilities on the graph. It does not change the resulting probabilities. So different triangulations won't give you different word error rate results or won't change your train parameters whatsoever. And finding a triangulation is an NP-hard problem, so we have to use a search. So triangulated, it just means that all cycles of length greater than or equal to 4 have a chord. So this graph is not triangulated because you have a cycle of length 4. And here you have a cycle of length 4, and there's a chord between two of the variables. So this graph is triangulated. And thought question, are these triangulated? The answer is the first one is yes, it's a tree. All trees are triangulated. The second one is no, it's not. There's a cycle here. It looks triangulated because it's full of triangles. But if you actually look at it, there's a 4 cycle around the outside. So it is not triangulated. And if you have an untriangulated graph, you can triangulate the graph by adding edges. You're not allowed to remove edges. And we don't need that slide. OK, so inference challenge 1 is that we're dealing with variable length sequences. If you recall, we have a DBN template that unrolls to match the number of observations. So we have a template, and here we have that template unrolled 3 different times. Problem is that the unrolled graph might be untriangulated, and it's not desirable to have to triangulate for each possible unrolling length. If you have 100 observations or you have 200 observations, you don't have to figure out a different triangulation for those different utterances. So the standard method, due to a caller off, is to find essentially a triangulation template. And then you just unroll the triangulation instead of unrolling the graph and then triangulate. So the first step in finding a triangulation template is you form a maximal clique, meaning you connect the variables together at the boundary between frames. What this is doing is it ensures that you have a point in which to connect your triangulation chunks so that the resulting graph is triangulated. If you look at the graph here, if I add this edge and this edge, this is connecting the variables that connect the boundary between frames. And then once you have the boundary, you just triangulate a single frame. So here's the single frame with just the boundary connected. And now we add some edges so that this chunk is triangulated. And then we unroll the triangulation. So this is this previous slide, just with this graph repeated 4 different times. OK, now we have the problem.
Sorry, Chris? Just a quick question. You're glossing over an issue of moralization.
I am. So yeah, so I actually added moralization.
Talk about it, but some people in the audience will know what that means.
Yeah, so I glossed over moralization. So all the graphs we deal with, we moralize first.
Thanks.
Yeah. Yeah, this user-defined boundary between frames may not be the optimal point to connect variables for the purpose of triangulation. And this was noted before. We have an algorithm in Darwich and that defines something called a forward and backward interface. And then you have an earlier paper that mentions that the interface might not be optimal. And then I have an example from Murphy 02. This is actually based on his example. It's not quite the same thing. But we have this template. And now we're going to form a maximal clique at the boundary between frames. Now we triangulate a single frame by adding that edge. Now we unroll the triangulation. You can see that there's, in 4 frames, we have 6 different fill-in edges. As mentioned, the problem for the user-defined boundary may not be optimal. And in fact, in this graph, it's not. So what we do is we perform a search to find a frame boundary that gives a better triangulation. And this is from our 03 UAI paper. And I'll give an example. So in this particular graph, the search will discover that we can find a boundary that just has a single variable. and then we rearrange the frames of the graph using this new boundary. This is the exact same graph as the previous frame. We've just rearranged the frame boundaries such that the boundary between frames is more conducive to a good triangulation. So we take the same steps as before. We form a maximal clique at the boundary between frames. No fill-in is needed. Now we triangulate a single frame. No fill-in is needed. And if we unroll, now we have a graph that's much simpler than before. So results. Theoretically, the improvement from the boundary search is unbounded. We can come up with an example that's a million times better if you want us to. In practice, often the user-defined boundary is good because people tend to put minimal information pass between frames, but it can make a big result. For example, in the syllable graph, the boundary search gives a 1.7 times speed up over the baseline boundary, which is a left and a right interface. Jason?
So are you guaranteed that the technique of, when you do boundary search, if in the user-defined frame you had, let's say, 10 nodes, I'm guessing that the boundaries that you look for will also have 10 nodes per frame?
Yes.
Is that guaranteed to give you the optimal solution of the unrolled graph?
So actually, no. So there's an additional parameter we try, which will look for a boundary in one frame, and then it will look for a boundary across 2 frames, and then it actually goes all the way up to 4. And I have seen
And that can improve.
that can improve it. In fact, if you, well, I don't know, it'd be hard to demonstrate with this little graph. Yeah, if you think about yet another variable that's down beneath this one, and you have an arrow going down, then you'd have to look across 2 frames to know to find the boundary up here.
Thanks.
Let me clarify something. Jason's question triggered this question. So yes, the total number of variables remains the same, but you may move variables from one side to the other, right?
Yes.
You move a variable from the right boundary. By moving it in here, you move your copy out over there. So
That's the game.
Yes.
and you're saying that there might be multiple ways of doing it and combinatorial with it.
No, that's actually that's what Chris said. And what I asked about is, are you even looking at enough options when you do that combinatorial search?
Okay.
Because it might be that you have to look, just looking at 10 nodes at once isn't enough.
Okay.
And you have to look at 20 or 30, or as it turns out,
Yeah.
they go up to 40 nodes at once if that
Yeah.
nodes to use.
Well, you can stop at when you have the number of nodes in your frame, because if you just take all the nodes in your frame
That's
and grab
nice.
them, that will be a boundary between the rest of the frames. So if you look at more than 10, you're grabbing all the variables.
Oh, okay, then I misunderstood something. But let's, I don't
Oh,
want
okay.
to
Maybe I can take that offline, but
Yeah, okay, thanks.
so yeah. So sometimes you have to look at more than one frame. And it appears that I am out of time. So let me just do the recap real quick. So you guys ask a lot of questions, which is great. Okay, so I showed you a DBN for burst noise suppression. Speech has a temporal pattern that is important for understanding. Noise typically does not have this pattern. Syllables were detected by finding maxima in a neural network posterior. And I have a DBN that counts the detections over the length of each hypothesized syllable. The baseline recognizer often recognizes burst noises as insertions. The syllable detector is able to fix many of these, and this mismatch is from this mismatch between classifiers is what allows the recognizer to recognize it as non-speech. And theoretically, this should work even if a particular noise is not present in the training data. And finally, I showed you this first method that showed that boundary search can repartition frames to allow for better triangulations in unrolled graphs. And that's it. Any additional questions?
I'll comment that you did try to present 122 slides, so it's not like we slowed you down.
Yeah, but lots of those are animations. So I put the animations on multiple slides. That is a lot of slides.
So since we took up a lot of your talk time questions, if there's something else that you want to tell us about briefly, it's only 5:30. We often run a little later than that. So.
Okay. Let's Okay, I think some of you have seen this talk, but maybe I can introduce it to everyone else. In much of the graphical model community, your graphs are made up primarily of random variables. So if you have a simple variable A and B, modeling the probability of B given A means a conditional probability table, which is a two-dimensional table. In many of the graphs that we use, they're primarily deterministic variables, meaning that the value of B is just determined by a function of A, such as B equals A plus 1. And all of the conditional probabilities of probability B given A are all 0 or 1. And if you know this function, you don't need a table to store the values of B. You just know the function. And keep in mind, even though it's deterministic, it still is multi-valued. It still has a marginal over its possible values. It's just that its conditional probability is deterministic. And this is just demonstrating this, that if you remember the triangle structure, the red variables are deterministic, and the white variable is the only random variable. And then the observation doesn't require a lot of computation. And this is the syllable graph again. Once again, the red variables, you can just see how many red variables there are. And then there's just a handful of random variables. So this is back to your question in that so many of the values are computable from the other variables in the graph.
I guess the question is this completely acyclic?
Yes. So Bayesian networks have to be acyclic, yeah.
And directed?
Pardon?
And directed.
And directed, yes. Okay. If you recall, minimal triangulation, actually I skipped the slide, but if there's any fill and edge that can be removed from the triangulation and the graph would still be triangulated, that would be non-minimal. If you remove any of the fill and edges and that causes the triangulation to no longer be triangulated, that's called a minimal triangulation. And when you only have random variables, optimal triangulations, according to the state space metric, they're always minimal. And then for those of you who know the elimination algorithm, these particular triangulations can always be found using the elimination algorithm. And I think this was assumed in a lot of places because there's lots of papers that use the elimination algorithm to find triangulations, but as far as I know of, we provided the first proof of this. Like I mentioned, there's a lot of work on using elimination to find triangulation. You can read all these papers. And then there are other methods that aren't elimination-based, but they also find minimal triangulations, such as the Para and Scheffler paper that uses minimal separators. So problem is that in graphs with deterministic variables, the optimal triangulation might not be minimal. In fact, it might be completely outside of the search space of the triangulation methods that are commonly used in the graphical model community. And as far as I know of, no one had ever attempted to use non-minimal triangulations for anything useful.
I have a quick question. Can you define what you mean by optimal?
Okay, that's the next slide. So we have a particular measure called state space. And I'll define what it is real quickly, and then I'll explain how it relates to the real graphs. So the state space of a single variable is just the number of values that variable can take on. The state space of a clique, so a clique is a set of variables that are all connected together, is just the product of the state spaces of the variables in that clique. And then if you have a triangulation with a set of maximal cliques, the state space of a triangulation is just the sum of the state spaces of its maximal cliques.
And then cliques are important because if there's a clique, it means that their joint probability doesn't factor. So
Yes.
in some sense, that's how many values I'll have to specify for the configuration anyway.
Exactly.
It may factor before you did the triangulation.
And
It might have factored, but the factorization doesn't actually help you
Yes.
in doing inference.
Yes.
And again, this is a very stupid naive question.
All right.
The reason you triangulate is because you only want every node to be a function of two variables.
No. So in fact, often the nodes aren't necessarily a function of two variables. In some formulations, they are. But we often have directed graphs that have variables with multiple parents. So you end up with functions over lots of variables. You triangulate because you just can't do inference without a triangulated graph. There are methods that do compute these probabilities without explicitly coming up with the triangulation. So, something like value elimination or search, but intrinsically they're doing these same connections. Darn it, where's my slide? If you think about dynamic programming over a set of functions, so if you have a function over, you have 4 functions over these 2 variables, and you want to do dynamic programming to say find just the marginal of one variable. If you sum out this variable, this is going to be a 3-dimensional operation. You're going to have to loop over the variable itself, then you're going to have to loop over its 2 neighbors. So you can think of a triangulation as forming a function over these 3 variables, because when you actually do the computation, you have to loop over these 3 variables. Then you do the next elimination, you have to loop over these 3 variables. Does that kind of make sense?
I'll ask you something.
Okay, sorry. Okay, so we have state space. And here's an example of state space when you only have random variables. So you have a very simple graph. So you have one function on A and B, and a second function on B and C. So these are your 2 maximal cliques. So the state space is the size of A times the size of B plus the size of B times the size of C. Okay? So.
And the runtime of inference algorithms is going to be proportional to the state space size, right?
Exactly. Yeah, and memory usage as well will be proportional. Okay, so now we have a state space with deterministic variables. We have to alter our definition of state space a little bit. And that alteration is when deterministic variables appear in cliques along with their parents, that deterministic variable does not contribute to the state space. So we have the same graph, but we've made the middle variable deterministic. So again, we have 2 functions, one over A and D, one over D and B. But this time the state space in the first term is just A, because the value of D is just some function of A, so we don't need any sort of special table to remember its probabilities. But in the second clique, A isn't in this clique, so we're doing some sort of calculation over D and B together. We can't directly determine B, so the state space of this clique is D times B. So in this next slide, we add this fill-in edge. You can view this as a triangulation of this graph. In particular, this is a non-minimal triangulation. And then we form one single maximal clique that's a function of A, D, and B. And now the state space over this triangulation is just A times B. And if you compare these 2 slides, this value of state space and this value of state space, depending on the cardinalities, depending on the number of values that D and B can take on, one or the other might be better, and you really don't know unless you check.
Excuse me, this is a deterministic function of A. The previous slide, A plus B should always be smaller than AB, right? This DB should always be smaller.
So D is always going to be smaller than A. So if this is a 100 value variable and you're collapsing it down to 2 values, this is probably better. If your deterministic variable is not that much smaller than A, such as example one of these counters in the triangle structure, it's basically the same size as A.
But I'm saying cannot be higher than A.
No, but this value can still be lower.
You've left off a sum edge, so suppose they're equal.
This is not bigger than it.
So even if D is smaller than A, this value can sometimes still be smaller. It just depends on how much the reduction is. And in fact, we can come up with, I can show you an example where a non-minimal triangulation, well, this example, yeah, if you make these big enough, the increase is actually arbitrarily big.
So for dying people in the audience, the lesson is that folding is not always a win.
And if you read the UAI paper, we define a few things. We define something called ancestral edges, and we invent an algorithm called elimination with extra edges. And then we present a number of heuristic searches based on ancestral edges, and these can find these optimal non-minimal triangulations. And in another paper, we presented a genetic algorithm. There was some work on triangulations using genetic algorithms that searched over an elimination ordering. RGA searches over the set of all possible fill-in edges. Theoretically, again, these methods give unbounded improvement. In practice, often we can do okay using standard methods. Elimination can find non-minimal triangulations, so if the graph is small enough, you can kind of find the right triangulation, even though it's not a logical elimination order. And on the syllable graph, it turns out the fastest triangulations actually are minimal from elimination, but it's not the case all the time. This is just a handful of graphs presented in the paper, and there's 9 graphs. You can see these 2 graphs were some pronunciation modeling graphs from Karen Lebescu, and we get over twice as fast compared to the best possible elimination triangulation. And then a couple of other graphs get smaller but significant speed ups. This is a articulatory feature detection graph from Simon King, and this is I forget what that one is. And then the GA. This is additional speed up over the previous results. Here's a asynchronous multi-stream graph, and again the feature detection graph. So it's on top of the other results because the GA is initialized using these heuristic results. So most of the time it does just as well. Doesn't always do as well because you try more options with the other algorithm. But
what's the MA heuristic?
Sorry, these are actually different graphs. So I tried a large number of heuristics, a large number of elimination heuristics, and a large number of my heuristics, and then timed them on the graph using real data, and it's the amount of speed up and wall clock time on these variety of graphs. What's that? Yeah, the heuristics is good most of the time. The GA is a little bit faster. Like it can find these by sampling a smaller number of triangulations. But yeah, the heuristics do okay. Okay. So
Jason,
should we?
do you think we've run over enough?
Probably a good time to stop.
Okay.
Okay. Thanks, Chris.
All right.